You know, every time you stream a movie, or send an email, or make a call to someone overseas, you're tapping into this secret world. It's a vast, unseen network of cables well over 1 million kilometers long, just wrapped around our planet on the dark, cold ocean floor. And this is the real backbone of our digital age.
So just think about it for a second. We live in this age of wireless everything, right? We talk about the cloud. We see satellite dishes everywhere. So how does pretty much all of our global data, we're talking 99% of it, actually get from one continent to another?
Well, here's the big surprise for most people. It's not beamed down from space. Nope. Satellites handle less than 1% of global data traffic. The real heavy lifting is done by a technology that's actually over 150 years old, just, massively updated. The submarine communications cable.
So here's what we're going to do. We're going to trace the incredible story of these cables, starting with the audacious dream of the Victorian internet. Then we'll get into the shift to a revolution of light. We'll dissect the anatomy of a modern cable, understand why it's the world's unseen backbone, and finally take a look at just how fragile this digital web really is.
Long before we ever had the internet, there was this burning desire to connect the world instantly. Back in the mid-19th century, these visionaries imagined stringing a wire across the bottom of the Atlantic, an idea that honestly sounded like pure science fiction. It needed immense capital, totally groundbreaking engineering, and a whole lot of guts.
What's really remarkable here is the sheer persistence. The first attempt across the English Channel in 1850, it failed almost immediately. The first big transatlantic try in 1858, led by Cyrus Westfield, worked for just a few weeks before it went totally silent. But they didn't give up. It took the largest ship in the world, the SS Great Eastern, and a way better cable design to finally, in 1866, establish a lasting connection.
The ingenuity of that time was just incredible. To protect the copper core from crushing pressure and all that corrosive salt water, engineers turned to nature. The key insulator was something called gutta percha, which is a sap from a Malaysian tree that was both waterproof and non-conductive. This was then wrapped in rubber, tarred hemp, and armored with a cage of iron wires. Amazing stuff. And here is the leap in capability. That first successful 1866 cable could transmit maybe 10 to 12 words per minute. A modern fiber optic cable can transmit tens of terabits per second. That's the equivalent of millions of HD movies simultaneously. The difference is just absolutely staggering.
All right, so the next great leap wasn't about making better copper. It was about abandoning it altogether. The future of data transmission wasn't gonna be in electrical pulses, but in tiny, controlled flashes of light. And this transition, it happened remarkably fast. In 1966, a physicist named Charles Cow theorized that a super-purified glass fiber could carry light signals over long distances, and he later won a Nobel Prize for it. By 1988, the first fiber optic cable, TAT-8, was laid across the Atlantic. And just a few years after that, the invention of optical amplifiers meant the signal could be boosted without being converted back to electricity. That just revolutionized transoceanic communication. At its heart, the concept is beautifully simple. Digital data, all the ones and zeros that make up everything you do online, is converted into pulses of laser light. These pulses then just race through strands of glass that are thinner than a human hair, traveling thousands of kilometers across the ocean floor at pretty much the speed of light. So what does it take to protect something as fragile as a glass fiber at the bottom of the ocean? Let's dissect a modern cable and see the incredible engineering that's designed to survive the abyss. Okay, let's build it from the inside out. At the very center, you have the delicate optical fibers. They're housed in a protective tube, and that's often filled with a kind of water-blocking jelly. Next, you get steel wires, not for communication, but for pure strength, to handle the immense tension of laying and recovery. Finally, it's all encased in a super tough polyethylene sheath. It really is a multi-layered fortress for data. But hey, even with the purest glass, light signals fade over distance. The solution? The optical repeater. These are basically signal boosters, about the size of a large suitcase, and they're spliced into the cable every 100 kilometers or so. They take in the faint light signal, they amplify it with a powerful laser, and then send it on its way, clean and strong. This is what makes a 6,000-kilometer transatlantic connection even possible.
So now that we kind of get the tech, let's zoom out and look at the sheer scale and importance of this global network. Because this isn't just about faster internet. This is the fundamental infrastructure of the modern world.
And we come back to this number, 99%. It really is that important. So when you think of global connectivity, don't picture a satellite in orbit. Picture these cables on the seabed, silently and reliably carrying nearly all of our international digital life.
And the reason is simple: bandwidth. A modern cable system has a capacity measured in tens of terabits per second. A satellite, by contrast, is operating in the gigabits per second range. The capacity difference is more than 1,000 to 1. There is simply no contest.
So what does this system power? Well, everything. Trillions of dollars in financial transactions every single day. The cloud services that run our apps and store our photos. Critical military communications. Your Netflix stream, your Instagram feed, that video call with family overseas, it all flows through these undersea conduits.
But for all its power and importance, this incredible network has a physical reality. It exists in a harsh, unpredictable environment, and you know what? It is surprisingly vulnerable.
Now, the surprising thing here is what causes most of the problems. It's not spies or sharks, though, yeah, sharks do occasionally bite them. The biggest threat, by far, comes from human activity. Over 70% of all damage is caused by fishing trawlers and ship anchors just dragging along the seabed. Every day, totally accidental events.
The good news is, we've gotten much better at protecting them. This chart shows the impact of one simple solution: burying the cables. In shallower waters, specialized plows actually dig a trench and lay the cable beneath the seabed, out of harm's way. And that single change, it reduced the fault rate by nearly 90%.
But accidental damage isn't the only concern anymore. As these cables become more and more critical, they become objects of geopolitical interest. States are now focused on the potential for deliberate sabotage, the threat of espionage through data tapping, and this strategic competition to control new cable routes, which, let's be honest, effectively means controlling the flow of global information.
And this really brings us to our final thought. We live in a world that feels increasingly wireless and virtual, but it's all built on this very real, very physical foundation. These cables are the hidden lifelines of our global society. And as our dependence on them just keeps growing, the question of how to secure them from accidents, from nature, and from human intent becomes one of the most critical challenges of the 21st century.